Hello and welcome everyone. Today we're really excited to bring back our NLP plus CSS 201 tutorial series. I'll introduce myself and my co-organizer, and then we'll introduce today's tutorial host. So hi, I'm Katie Keith. I'm a postdoc at AI2. Very excited about NLP plus computational social science. And my co-host or co-organizer is Ian Stewart.
Yeah, hi, I'm Ian. You probably seen me before. I'm also organizing this series. I'm a postdoc at Michigan, where I also do NLP plus CSS, and looking forward to learning about causal inference today.
And we're very excited to have Dhanya Sridhar with us today, who's an assistant professor in the Department of Computer Science and Operations Research at the University of Montreal and a core academic member of MILA, the Quebec Artificial Intelligence Institute. She did a postdoc with Dave Bly at Columbia and her PhD in computer science at the University of California, Santa Cruz. So with that, I'm going to turn it over to Dhanya, who's going to explain the tutorial. And please do put questions in the chat. Ian and I are going to monitor that. And then feel free also, Dhanya has said, to raise your hands or just interrupt with questions throughout.
Okay, awesome. Thank you, Katie and Ian, so much for inviting me. And thank you all for joining us today. I'm really excited to talk with you all a little bit. And let me go ahead and start sharing my screen. Okay, so I'll be talking about, as Ian and Katie sort of alluded, about causal inference. And in particular, I'm going to talk about causal effects of properties of text or properties of language. And so I'll give a little bit of background on the work I'll be talking about today. So I'll mostly be focusing on this paper that we published in 2021 on causal effects of linguistic properties. This is actually a pandemic project with a whole bunch of different collaborators. And so as you see here, I've got a link here to a really excellent GitHub repo that you can use to reproduce all of the experiments and check out the implementation that we used in the original paper. Today, the repo and the demo that I'll be taking you all through will use a slightly different piece of code and a slightly different algorithm. But if you'd like to just kind of read the paper and reproduce our studies exactly and see our data, you can go to this excellent repo. So I highly recommend it. And I mean, in this modern era, everybody Googles everybody else. So I don't need to necessarily write my email here, but there it is in any case. In case you have further questions and you want to chat with me after the tutorial, we can always take the more elaborate questions and maybe the philosophical musings offline. Okay, so what do I even mean by this rather big seeming question of causal effects of linguistic properties? So I'm going to motivate this phrase with a concrete example. So the motivating example is going to rely on the Consumer Finance Protection Bureau. So in the US, the CFPB allows consumers like us to write complaints about a whole bunch of different financial products. Here's an example. Sorry, I think somebody has not muted themselves. So the Bureau collects a lot of complaints on various financial products. This includes lots of things, but a common one is banks, like checkings or savings accounts. And so people write complaints. So about a year ago, I grabbed this example literally off of the CFPB website. So these are real examples of the kinds of complaints people write. So you can see that this is a fairly irate complaint. And the Bureau also records this variable called timely response. By the way, can everybody see my screen okay? Are you seeing the Zoom bar at the bottom and not able to see the text? Okay, good. Awesome. So the CFPB collects this variable as well about whether or not the complaint was resolved by a CFPB official in a timely manner. And so we might ask whether the politeness of the complaint affects the timeliness of the response, right? So the speed of the response. Okay, so this is an interesting question. And let's just say more about the setting. All we observe in this context are a bunch of complaints and a bunch of labels of this timely response or not indicator. Okay, so this is our training data. So at this point, one of the first observations we have here is that a property of interest like politeness is actually latent. And a common approach that we might take as analysts of text data is rely on some sort of existing lexicon or a classifier. And so what I mean by classifier here is somebody else on a totally different corpus may have trained an algorithm to take text and predict politeness. So maybe they, in their separate context, had labels about politeness. So they trained a classifier, but now all you can do is put text through some sort of machine that gives you a noisy signal about the politeness status of the document. Okay, so a lexicon is a great example. It's just a list of words. And so we might have a list of polite words and reference against that list whether this document contains a whole bunch of them. And we might aggregate that information in some way. And in some sense, we'll produce this label T proxy that you can think of as like a noisy, like a computer approximation to how a reader might perceive the text. Okay, so in this talk, I'm going to basically answer 3 questions. So the first is talking about how we might even formalize the meaning of effect of politeness on response. Okay, so first we'll just say, what does that even mean? And then we'll ask whether it's possible to recover these kinds of effects using especially a proxy of politeness. And if it is possible, then how are we going to do it? What is a bit of pseudocode or an algorithm that can actually estimate this effect with observational data? Okay, so first we're going to answer this question about formalizing causal effects. And so to do this, I'm going to pivot away from text entirely and talk about perhaps a more standard setting in which causal inference as a field has really developed. And so this is the clinical setting where we might have new therapeutics like an antidepressant, and we might wonder whether an antidepressant has an effect on reported depression levels. Okay, and so here I've used little pictographs to represent a taking a new drug therapy or not as a binary choice. And there is some outcome of interest. So I've represented reported depression levels with some measured outcome Y. So what does cause even mean, right? What does this word mean mathematically? It means that if we change a variable X, then X causes Y if manipulating X changes Y in some sense. Okay, and that sense is exactly what I'm going to build up to here. So we need a formalism for what manipulating means and what changes means. And that's what we'll see in the next few slides. So let's introduce a few more variables here to fill out this whole story. So the data generating process of these variables, such as whether or not somebody chooses to take a new antidepressant and what might happen to them, involves a whole bunch of other factors that might be very, very complex in the relationships they have with one another. We'll call them Z. And so these are the 3 variables. And so what we're seeing here, and we'll see this throughout the talk, is this language, this kind of cartoonish version of a graphical model that tells us which variables are associated with one another. Okay, so in this case, what we're saying, or what this tells us, is that the variables, whole bunch of complex factors, affect whether people take the drug or not. They also affect how people respond to the drug, and then the drug itself might have some effect on recovery. And so nature, it really kind of controls this process, and it hands to us distributions of these variables. And that's what we think of as observational data. So causal questions, I said the words manipulating X or manipulating a variable X. What it kind of means is we'd like to intervene on this system and administer the antidepressant to everyone. Okay, so I've indicated that here with this breaking of the arrow that goes from the factors z to the variable y, the variable t, sorry. So here what we're doing is we're disallowing the natural process by which people choose to take therapeutics or not. And we imagine, okay, this is all totally hypothetical. We imagine intervening and administering this antidepressant to patients, to all the units of study. This creates a new distribution, okay? And I'm going to index this distribution. I'm going to give it a name by using this variable, this operator called do. And all it says is I'm going to consider the distribution of outcomes in a world where I've intervened on the treatment variable and set it to 1. Okay, so do this fancy notation does nothing more than just index a new distribution, one in which we've broken that arrow between z and t, and we've set the value of t to a constant. Okay, so this is nothing more than a distribution, one that we'd like to sample from if we want to understand whether t causes y. Okay, that's what's special about this distribution. And if you've seen causal inference before, you may be familiar with this language of potential outcomes. And so the connection here is that a potential outcome you can just think of as a special variable that's sampled from this distribution. Okay, so now we talked about interventions, but we didn't connect it yet to effects. So now going back to the question of what is the causal effect of the antidepressant on depression levels, especially when we're trafficking in binary treatment variables where you either take the treatment or you don't, a common question or a common mathematical question to look at is this average treatment effect. Okay, so to formalize effects, we simply consider contrast in the average outcome across two distributions, one in which we intervene and give everybody the treatment, and one in which we intervene and we prevent everybody from not taking the treatment. Okay, so I mean, really, this is the simple picture here. So we are just contrasting the means of two different distributions. We say that a drug has a strong positive effect on y if this difference is a number that's away from 0. Right. So the thing about this setting that we should really keep in mind is that everything is kind of clean here, right? So we have recorded whether somebody takes a treatment or not. Treatments are kind of it's clear what it means to intervene and give somebody a drug. And the problem is that now when we translate this mathematical formalism to text, it's not totally obvious what it means to intervene on some property of text. Okay, so that's the first thing that we're going to investigate. So we want to formalize this question: what is the does this politeness affect response time? And we don't really know what it means to intervene on a document and change its politeness. So to kind of make this concrete, we're going to study the structure of this problem. So first thing, we have here one agent. We have a reader. The reader looks at complaints and they perceive things about the complaint, such as the topic that's written about, the style. They perceive whether it's polite or not, and they use all of these perceptions as inputs to deciding how quickly they'll respond or not. Okay. So there's a bunch of factors that go into their kind of decision-making process. There's another agent. That's the writer of the text, right? That's the writer controls the generative process of the text. So they decide whether or not they're going to be polite. They have a topic in mind. Of course, this dotted arrow here represents the idea that whether I'm angry or not and what I'm going to write about may not actually be kind of independent choices. So these are kind of dependent variables, and these are the ingredients that go into generating the text in the first place. And as we said earlier, there's this other object floating around here. That is the proxy that we're going to produce about politeness by applying a lexicon or a classifier. So we have, lots of different characters in this play, and we don't know which one we're going to intervene on to define and formalize a causal effect. And to get there, first, I just want to note an interesting symmetry between the reader and the proxy. And the symmetry is that in both cases, in some sense, the text kind of blocks off all the other paths by which the politeness perceived by the reader can inform the outcome. Okay, so we see that in some sense, for both the variable T reader and T proxy, there's the symmetry in that kind of all paths that lead to the outcome have to go through the text. That's not the case for the writer, right? So the writer, there could be arbitrary, dependencies, arbitrary kind of latent, unobserved things that make it so that the intended politeness and all the other things that a writer intends are arbitrarily dependent on one another. Okay, so there's a whole bunch of kind of common causes that could affect these things that we just never get to observe, but that's not quite the case for T reader and T proxy. So now the question is, from which agent's perspective should we consider interventions? And we'll see in just a few minutes why this is going to be desirable. But in this paper, we say we're going to concretely consider the effect on response time if we imagine changing the perceptions of the reader from forcing them to perceive the document as being polite versus impolite. Okay, and this is actually going to end up with nice properties in just as we'll see just a little bit later in this talk. So the takeaway from this part of the talk is just to sit with this idea that text is a complicated object because it is both the rendering of the writer and it's read by readers in order to make decisions about text. And so step one, formalizing effects is not obvious, but what helps is kind of very explicitly articulating the whole structure of the causal model, right? Just articulating all the ingredients that go into describing the world at hand. So now we've talked about effects, but we haven't said anything about actually calculating, interventional quantities with data. So I'm going to again go back to the clinical setting here to ask, when is causal inference even possible? To appreciate why this question is so, difficult and challenging, let's just kind of consider that I certainly cannot, for every single person, both give them the drug and not give them the drug, right? I certainly cannot, in some sense, right? I can't simultaneously sample from both of those interventional distributions that we're interested in. I could randomize and give some people the treatment versus other people, I prevent them from taking the treatment, but I cannot, for any given unit, do both of the interventions. So in some sense, causal inference is fundamentally hard because we have to, at some point, draw conclusions about an unseen world for which we have no way to realize data. Okay, so I alluded to this. So one way to kind of mimic loosely the structure of an interventional distribution is by randomizing who gets treated and who doesn't. Okay, so we might do this. So, in interventional distributions, we sever that link between Z and T. Here, we make T kind of independent of all of these other factors by simply controlling and randomizing treatment assignment. And it turns out that in this setting, we can just calculate the expected difference in outcomes between the two groups. And this is how we can calculate causal effects. But that's a special case, right? And in the example that I described, it's not totally obvious how to randomize, for example, perceptions of politeness. And so we're going to need to go with a different strategy. So we're going to consider the setting where there are a whole bunch of complex factors that control why people choose to take treatment or not. And in this setting, we see that, I sort of alluded to earlier that maybe in the interventional case, if we could actually calculate the true causal effect, we'll see that there's a strong positive effect of the antidepressant. But if I just, in this observational setting, compare the average difference between the treated and untreated, there's no effect. So what happened? If we squint at the data further, what we may see is that the treated group and the untreated group in observational data may not be the same. They may not really be comparable. And this is because these factors that I described, they act as confounders, right? They are an alternative explanation for why there exists some correlation between the treatment and the outcome. Okay, so they generate an alternate kind of source of correlations. Correlations are all that we observe, right? We don't get to observe interventions. We only get to observe associations between T and Y. And from that alone, we can't tell apart what is the causal effect and what is this confounding effect. So there's this idea, this is well studied in causality. And so there's been a fix proposed for this under some assumptions that we'll talk about later. But informally, what the idea is to group the data by the confounders. So you group everybody by severity, and then within each group, you look at the treated and untreated and calculate the expected difference in outcomes, and then you average that difference across all groups. Okay, so informally, that is what is causal adjustment. We'll see a slightly more formal version of this later, but it's fairly intuitive. It's kind of saying, okay, after you've kind of accounted for these confounding variables, whatever difference is left ought to be explained by the causal effect. Okay, so let's go back to our graph here, and let's kind of consider what are the causal assumptions here. What are our confounders in this case? So we might think that the reader perceives a whole bunch of other properties, right? They perceive the topic, for example. And it may be the case that complaints about banks just happen to be generally perceived as impolite, and on average, they receive slower responses. So here, the sort of perceived topic is acting as the confounder. Okay, and so this topic that the reader perceives is a function of the text. And so one of the key things to notice in this case is that the text itself kind of acts as this one big confounder blob. Okay, so we might think that, okay, we have some hope here to use it for causal adjustment. Before I talk more about what causal adjustment might look like in this context, I want to be very explicit about what's being ruled out by this assumption that the text suffices to account for all sources of confounding. Okay, it seems like magic, but I want to kind of make it very clear that this is a strong assumption. So we're kind of like buying results by making a pretty strong assumption. And what are we ruling out? We're saying that there can't be any other kind of common causes of the reader's perceptions of politeness and the outcome. Okay, so there can't be other sources of correlation between why people perceive a certain topic and why they perceive politeness. And there certainly can't be other common causes of a person's response time decision and their perceptions of politeness. So for example, this could rule out things like maybe if the reader is very, very impatient or something like that, or they have a certain personality trait that makes it both more likely for them to perceive politeness and respond slowly, then this is going to affect our causal inference. And so, we ought to sort of be very clear about what we're giving up when we make causal assumptions. Okay, so we are for now going to proceed by disallowing these paths. And I said that there is a slightly more formal way of writing that causal adjustment that I just described in words. Here it is. We average over groups of the confounder variable, consider the expected difference within groups, and then average over groups. Okay, it's just a slightly more technical way of writing it. And as I wrote earlier, we can replace, instead of kind of adjusting for the full text, we can adjust for just the other perceptions that also affect response time, the variable that I'm calling Z reader. And if I write it in this mathematical way, it leads to kind of an important insight about what kinds of confounding we can consider and what we can't. because we see here that we're considering two different quantities, right? One in which we condition on somebody perceiving the document as polite and some set of properties existing in the document. And we're considering a case where the reader perceives the document as impolite and the document has the same exact properties D. Okay, so what this means is, imagine that somebody handed to you the confounders and they said, these phrases that I've highlighted in red are also confounders in our problem. It's going to be pretty impossible to imagine a reader perceiving this document as being polite while still having those phrases that I've highlighted in red, right? Like you can't imagine somebody seeing the phrase evil people start banks and then somehow thinking, this is a really nice complaint actually. So, but on the other hand, right, you can imagine that if the confounders were just kind of the perceived topics, right? So words like bank and overdraft fees might clue you into the topic, but you can totally imagine somebody writing, say, a polite version of a complaint that uses the same phrases, banks and overdraft fees. So the insight here is that there's another assumption that's buried in all of this causal inference, which is that the kinds of things that we're allowed to consider as confounders have to be orthogonal in some sense. They have to be different. They have to be quite distinct to politeness itself. Okay, because we have to be able to imagine both impolite and politely perceived texts that have those same exact properties. Okay, so we've said something about recovering the causal effects with the true perceptions of the reader, right? Which, as we said, we don't have access to. So now we're going to kind of consider this other character, T proxy, which in some sense, now we can see it's like a computer version of T reader, right? It's kind of like maybe a very noisy version of what we might think a reader is going to perceive when they read the document. Okay, so the first proposal, maybe the most obvious, straightforward seeming thing to do, is to calculate the average effect among the documents that the proxy says are perceived as polite and those that the proxy says are perceived as impolite. And this is kind of surprising that I'm going to tell you that this proposal is not very good because the proxy is not exactly the same object as the unobserved perceptions of the reader, right? It's a variable that is simply looking at scanning the text and making predictions about some properties of the text. And it turns out that a problem can arise around measurement error that induces a bias that is very much like what Z reader is doing. Okay, so it turns out that the errors that T proxy can make, right, might be systematic. So the proxy might be doing better or worse for certain topics. And it might be topics that also encode information about timely response or not. So measurement error has a signature that's very much like confounding bias, even though they're not exactly the same thing. Okay, so the proposal that I'm going to propose here is not very, shocking. It's we do a very similar adjustment to what I showed earlier when we had T reader, but we swap in the proxy variable for the true perceptions of the reader. Okay, and this is still, as of now, I still haven't said how we can even do this because Z reader is unobserved, right? We still haven't solved the problem of how are we going to extract these other things that a reader might perceive that confounds our causal inference. But before I say how we're going to do this, I just want to kind of say what is the main result of this paper. Why am I proposing this particular estimator for the causal effect? It's because we can kind of come up with a nice theorem here. There's a lot of math. I'll talk through it. So we'll be bold and not be daunted by this. But the high level is this theorem is about attenuation bias, or bias attenuation, sorry, which says that there is what it says that is that even though we're using a noisy version of politeness as perceived by the reader, we might be able to recover a estimated causal effect that still has the same sign as the true effect. It may be lower in magnitude because of the error, right? Because of the proxy may not be perfectly sort of high fidelity for the reader. But what we're going to lose is magnitude, but not sign. Okay, so that's quite important. So you're never going to kind of reverse the sign of the causal effect and say that politeness worsens response, it makes response time slower, when in case the opposite is in fact the truth. Okay, so what are these components? So the first thing that I've highlighted in orange here, this is like the per group causal effect. This is, or the per group difference. This is like within each kind of group of these confounding variables C, this is the expected difference in response time. Okay, so that's one of the ingredients in the theorem here. This is the bias term. And then there's this other kind of term that relates to the mismeasurement of the proxy. So it's kind of the false positive rate and the false negative rate of the proxy. And so it turns out that if the proxy is a better than random, okay, so the proxy has to be better than random, and B, in each group, the causal effect is going in the same direction. It could be of different magnitudes, but it has to be in the same direction. Then this entire term ends up being smaller in size than the true causal effect. Okay, so that's how we end up with this attenuation result. And again, you know, we're asking for some stuff here, right? So you know, in particular, I said in each group you expect the causal effect has to be the same in direction at least. Depending on the setting, an analyst might say that's too strong of an assumption, and that is exactly the kind of statement that an analyst ought to make before using causal effect estimation techniques. Okay, so basically, I kind of think all of these assumptions and causal graphs that I'm articulating, they are a blessing, not a curse, because they really force us to reckon with, you know, what it is we are assuming in order to get these nice results. Okay, so now let me tell you, if it's possible, how can we do it? And actually, let me just, I forgot to kind of say what are the two lessons from this theorem, because that's kind of what matters. It's not the statement of the math, it's just what does it tell us to do? It says that try to estimate and adjust for these confounding aspects C. And if you commit to doing that, then the best thing you can do is try to minimize the proxy error. Okay, so before I kind of, maybe I'll say one thing where very quickly, you might kind of wonder, right, like what does it mean to make an accurate proxy? Because I don't have the true labels about what the reader's perceiving on the data set where I'm estimating causal effects. So how do I evaluate whether I have an accurate proxy or not? And this is really about sort of analyst judgment. So for example, in the case where you used a lexicon, like I was kind of giving this example, then we might believe that lexicons are high precision, but low recall. So we might want to do some sort of kind of lexical induction, whereby we relabel some of the texts that the lexicon considers as, you know, negatives, and kind of induce basically more of a semantic similarity across text. So we're going to have to appeal to domain knowledge is my key here, because indeed there's not a way in this case to kind of appeal to kind of standard holdout data accuracy metrics. Okay.
Sorry to interrupt. Would you mind taking a question now, or would you rather wait until you're finished with the presentation?
Now is great. Now is great.
Okay, cool. Yeah, it looks like we have a question from Ian, which I'll read out now. He's asking, or they're asking, I've been wondering about the time of day or day of week when requests are written? Isn't it possible that requests written late in the day are less likely to be polite, less likely to have timely responses? Do you observe the time of requests in this data? Either way, could this confounder cross from writer to reader? So I don't know if you wanted to answer that now or save it for later.
Good.
Go
That's
ahead.
a very good question. Let me answer that now. I'll go back slightly so we see the graph here. So I think what's special about this structure is that the thing that really passes from writer to reader, this is my view, is going to be the text, right? Like the text is all that kind of is an overlap in terms of characteristics between the writer and reader. But to your point, it could be the case that time of day affects how people perceive the things they read and how they respond to them. So kind of going off your same example, maybe late at night, people are just kind of grumpy and tired and they are sensitive to phrases in the text they read, and they'll think that things are impolite when they would have maybe thought differently at other times. And they're like kind of slower to respond. So it could be the case that there are these other kinds of confounders that I said, like we have to rule out for the case of this particular setting. So that's a very good question. And yeah, so I think it's kind of important to consider that on one hand, the reader-writer dichotomy has bought us something. It's ruled out some kind of confounders because we have this really nice property that like the thing that passes from reader to writer is just the text. But on the other hand, we're also asking ourselves to not kind of consider these other peculiarities in how people might both perceive stuff and respond. And right, that's exactly the price of doing business here. Okay. Okay. So all I wanted to say about related work here is that it's important to kind of make clear how this is quite different than what's been done before. So historically, in the context of using proxy variables in causal inference, the tack has been adjust away the proxy noise somehow. And to do this, you actually need a full measurement model for how the proxy relates to the truth. Okay, so it's quite a strong amount of knowledge to know, but if you have it, the aim has been to use that knowledge to kind of invert the measurement bias. On the other hand, the other way that causal effects of text have been studied without proxy variables has been through randomized experiments and with kind of stronger parametric models, whereby we kind of model all the sources of confounding more explicitly than we do here. And so where this work sits is, on one hand, we've got the proxy variables, and we're not going to assume that we know exactly the relationship between the true label the proxies correspond to and the proxy. But what we're going to do is we're going to appeal to NLP methods to try to extract features that capture that confounding information so that we can adjust for Z reader, like I described, and we can get a causal effect estimate that has some nice properties in that it is kind of got this attenuation bias quality to it. So I said something about we're going to use NLP. How are we going to use it? The idea is that to capture the parts of text that that are confounding, we're gonna consider this adjustment formula and think, what is it that confounders do? What is the signature they leave? And the signature that they leave on the data is that a confounder can be used to predict the expected outcomes well, given the treatment. Okay, so we can use that signature to construct a prediction task that tells us when a variable does this task well, it is capturing confounding information. Okay, so in the paper and then in the GitHub repo that I mentioned earlier, what you can see is this algorithm that uses BERT. Okay, so at a high level, the inputs to this algorithm are going to be the proxy, so the predicted politeness status of a text given by a lexicon or some other separately trained classifier, and the text itself. BERT produces for every document or every sequence of tokens one embedding, and we're going to train this embedding to predict the expected outcomes Okay, so, and you can do this, for example, by minimizing cross entropy loss. If you have binary y, you can also minimize squared error. If you have continuous y, there's many things in between for each group, right? So the key here is there's two classifiers that we train. One on the document that the proxy has labeled as being polite, and a separate classifier in the document the proxy has labeled as being impolite. The hope is that by conditioning on this politeness variable, this politeness information as well, we encourage Lambda, the embeddings, to learn all the other stuff that's predictive of response time other than politeness. Okay, so let me also kind of flag this general framework as a big opportunity to do research in NLP as well. So here we're using this kind of inductive bias to guide the embeddings towards good information in some sense, good being like good for valid causal inference. But this is just one kind of first pass at it. So there's a lot of work to be done on kind of nice architectures to be able to extract confounding information in particular. Okay, so now that I flagged that, I'll just say that we'll see this in the demo more, so I'm not going to dwell on it. But these predictions, these classifications that the model makes, they can just be used to estimate causal effects in a very simple way. So I said now the answer to the three questions I kind of said I was going to focus on, and so now I think we're almost at the demo point, and so I'll just kind of give a high-level glimpse teaser about where we're going. The problem is that, unlike other problems in NLP, here we don't have ground truth data. So ground truth here would actually be a causal effect, a known causal effect of some variable, some aspect of language on some outcome. We typically don't have these lying around. So what we're going to do is we're going to use semi-synthetic evaluation. And how we're going to do this is we're going to take a corpus of text that has some treatment label of interest and also encodes some confounders. So to be concrete, we have Amazon reviews, and we have with every review the rating that the writer produces. We're going to assume that a reader of the review is going to look at the number of stars and perceive the sentiment of the writer based on the number of stars. Okay, so we can use, and we can binarize this by saying 4 or 5 stars versus 0 or 1 stars, and this can become our treatment, which is going to be perceived sentiment of the review reader. And we have other metadata, such as product categories. Okay, and it turns out that the product category is a thing that you can definitely extract from text. Okay, so you can kind of run that experiment and see that, yeah, you can predict typically the product category from the text itself. So what we're going to do is simulate an outcome that depends on the perceived sentiment as captured by the ratings and by the product category. Okay, so we take the metadata that we have here, the product category, and we'll just turn it into a confounder. We'll just create outcomes that depend on both of these things, so that from the correlation of perceived sentiment and this simulated outcome alone, we can't tell apart the causal effect. Okay, so here we fix the causal effect as some kind of ground truth quantity, and we're going to see as we kind of crank up the knob and allow the confounder to be increasingly the thing that dominates the outcomes that are simulated, we'll see how well our different methods recover the causal effect that we fixed. Okay, and so so now I'm gonna just kind of give an example of this with code. And before we go there, let me just, this is basically going to be the end of my talk, and so let me just summarize what all we learned. Of course, I think this is kind of I don't need to belabor this with this community, but text data presents a nice opportunity to extract all of these latent variables that we want to reason over causally anyway. And with the amount of text data that we have, we can basically kind of infer all of these things about people. Defining causal questions, however, in the context of text can be very challenging, not totally obvious. But by articulating the causal structure of the problem, we're able to exploit some asymmetries, for example, like the asymmetry between writers and readers, to both kind of come up with causal assumptions and also to help us even just formalize effects. Okay, and then, like I said, there's a lot of opportunities for new research here, not just for new research designs around randomization or pseudo-randomization, but also new estimation methods and new evaluation schemes. Okay, so we're going to see just one today, but I, sort of would like to leave everybody with a call to action to kind of invest in this area of research. Okay, so now I hope that we've got a completely run demo here. Okay, seems like we do. So now, hopefully everyone who wants to check out the demo is able to open it and have a look. I'm going to talk through this in as much detail as I can, given the time constraints. But hopefully you can kind of go through and read it and run it yourself, and also, try your own data, right? So if you've kind of brought your own data, I've tried to give some tips on how to use data other than this particular semi-synthetic example. So to remind ourselves, I've included some data here that I've already pre-processed. You can look, like I said, at Reed's very, very nice repo to learn more about how we do the simulation. But here I've done it already. I'll just kind of talk through the steps of what happened here. So these are Amazon reviews about, I think, like CDs, MP3s, and albums. And the outcome you can think of, even though it's simulated, as a binary indicator for somebody buys the product or not. And the idea is that we are going to use, like I said, the true perceived sentiment and some other variables to simulate these outcomes, right? Thereby kind of simulating confounding. Here, the treatment is going to be whether the product reviewer gave a rating of 4 or 5 versus 0 or 1 star. And we're assuming basically that a reader who would look at a review like this will perceive the review to be positive if they see 4 or 5 stars and negative otherwise. So a simulated purchase is going to, in this world, depend both on whether a reader thinks the review is positive and whether a review is about a CD or not. Okay, so basically what I'm saying here is we have this simple world in which people buy stuff both because they might see they might perceive a review to be positive, and if the product is talking about CDs, they might buy it anyway because they just, in this world, people just like CDs. So from the correlation, right, between the ratings and the simulated outcome, we can't tell the causal effect apart from the confounding effect. Okay. And so let's just look at the kind of simulated data that I have here. And I'll also show you what kind of things we can use as lexicons. Okay, so here we have a bunch of, forget some of these variables. We have the text. In this case, we have the true rating of the binarized version of the stars. And we've generated a proxy, okay, using a lexicon, which I'll show you in just a second. We know again, we have ground truth about whether this is about a CD or not, right? Because we kind of know the category of the product. And we have a simulated outcome. And I also have these counterfactual outcomes. I'll say more about that in just a second. Let's just see here what we might be able to do. So here is just, for example, this lexicon, this is just a list of exhaustive, albeit list of positive words. And so we can cross-reference, we can just see if the text contains these words, and then there's many ways to aggregate this information. So we can, we can say if the text contains any positive word, then it's positive. There's a lot of ways to do this. So can you use your own data? Yes, absolutely. So as we'll see in the rest of this demo, the key ingredients, right, to actually running the adjustment technique are the text, t-proxy, and the outcome. Okay, so those are the relevant columns in this data frame. And you don't obviously have to have a simulated outcome. You can have a real outcome over which you had no control. I just kind of called it YSIM because it's YSIM in the data frame here. Okay, so the thing that if you're going to use your own data that's not simulated, what can't you do? You obviously can't calculate the true causal effect. So here, because we were able to generate the outcome for every single text, we can generate both the outcome had the text been treated and had the text not been treated. Okay, so I mean, this is as simple when you have the simulation model. This is as simple as setting the binary treatment indicator to 1 and then to 0, and then just evaluating the simulation model. And then, as we said, by definition, the ATE is just the expected difference in potential outcomes. I think I kind of forgot a square bracket here, which I'll fix later in this equation. Ignore that. But here we see by doing this calculation, which is one line, very simple, the true ATE is around 0.15. So what is it saying? Your chances, your probability of buying a product increases by 0.15 if the review you perceive as being positive. Okay, so that's actually in terms of on probability scale, that's a big, fairly big effect. So as I said, what goes wrong if I just look at the correlation between the proxy label and the outcome? Okay, this is not even the true label. This is just the proxy. After the proxy has suggested to us whether a review is positive or not, I can just calculate the difference in the two groups. And we see here that the average difference, right, taking the sample average, you kind of really end up underestimating the true ATE by nearly half. Actually, maybe more than half. And so now we're going to work with the adjustment that I talked about, and we're going to follow some ideas from this other paper called Causally Sufficient Text Embeddings. And in Reed's repo, we appeal to BERT. In this demo, I could not fine-tune BERT in a reasonable amount of time to be able to run it live. So we're actually going to use topic models. And here's the idea. It's pretty simple. We are going to, as I said earlier, we're just going to swap in topic models instead of BERT. We're going to train a topic model. In this case, we're training it using variational autoencoders. And the encoder is going to take a document represented as a bag of words and produce its topic proportion. Okay, and we'll call that its representation. And the representations have to do three things well. They have to model the log probability of the document. That's why that's how we know they're going to be faithful reconstructions of the text themselves. And then they have to predict the outcomes for both groups of documents, those where the proxy says positive sentiment and those otherwise. Okay, so the pseudocode is kind of, it takes these 4 high-level steps. I'll let you read through that on your own time, because we can kind of see the steps represented as we go through the code. So first, we represent our documents as a term frequency matrix and do a little bit of pre-processing to get rid of documents where the total term count is 0. Then we fit a topic model to do the tasks that I described. So in this repo, I have included code for a topic model and a way to train it using variational autoencoders. If you're familiar with this, again, the paper that I referenced up here, called Causally Sufficient Text Embedding, says more about the structure of a topic model and more about the way to train these topic models. But at a high level, what you can imagine this object doing is trying to learn a set of topics that are good at reproducing, at estimating the empirical term frequencies, right? You're trying to figure out a vector that represents for every document what topics it talks about. And then you're trying to understand for each of these latent topics, which words that topic prefers, so that when you multiply these two things together, you can approximately reconstruct the term frequencies that you do observe quite well. So we're going to fit this thing with 10 topics. And there's some parameters that the code sheds more light on. But basically, we are going to train it with mini batches, and we're going to do 300 gradient descent iterations. And then we are going to ensure that we predict the outcome label for both of the groups of documents. Okay, so the key task here, the key prediction task, is to do this supervised prediction task of the outcome. This has been done now, and like I said, now, regardless of whether or not the document was originally treated, i.e. received a positive sentiment prediction by the proxy, we put every single document through these two classifiers. Okay, getting for every document a prediction of how it would have behaved had it been treated and how it would have behaved had it not been treated, right? So sorry, to kind of be more concrete, we're going to understand the purchase probability had the document that the review been treated and otherwise, right? So the models that we train do nothing more than approximate counterfactual outcomes. And so we can use these, right, to make predictions for every review. And then when we take the mean of that difference, we end up getting the estimate of the causal effect with the proxy. Okay, so this quantity we see is much closer to the true AT. In fact, I think it's like very, very, very close. You may notice it's slightly it's a slight overestimate, and you might think, like, how does this play with the theorem that I talked about earlier? So this is with finite samples. Okay, so like the theorem really is in the realm of like infinite data, and in finite samples, you kind of like probably approximately satisfy the theorem. Okay, and then the nice thing about topic models in this case that BERT is not as readily amenable to is we can do things like inspect the model and look at the fitted topics, and then we can go back and, for example, kind of fine tune or I'm using fine tune very loosely here. We can go in and adapt our model based on our interpretation of the model. Okay, so that's all I have in terms of this tutorial. I kind of the setting that I demonstrated with this pre-processed data, it is simply one of the many settings that we studied in the context of the paper itself. So it's just one of the simulation settings. And so again, like I said, the repo with the Breeds code is able to reproduce all of the experiments we ran and shows how you can use the simulator to generate a whole bunch of different kinds of confounding levels. Okay, so maybe I'm going to stop the share here. I've already kind of gone above time, and if there's time for a few questions, I'm very happy to stick around and answer them.
Yeah, we are a little bit over time, but if Danya's happy to stick around, if anybody has any questions and wants to unmute, it sounds like we can take a couple before we wrap up.
Hi, David Lang here. One thing I'm just sort of curious about with this methodological toolkit, do you have any insights on how it can be adapted to quasi-experimental settings?
Awesome, yeah. So I think that's a great idea. And I think there's, I think a nice paper to read is I referenced it in the talk. I'm happy to share my slides so you can see it. But Grimmer and Fong had a recent paper about an interesting kind of randomization you can do here, where you obviously can't randomize who perceives what, but you can randomly assign text to readers. So they have one kind of like intent to treat kind of setup. So one could imagine that as being fitting into this kind of like instrumental variable quasi-experimentation scheme. And they don't do this, but I think there's an opportunity to combine ideas around proxies with their kind of framework. And so what might be quite kind of interesting is to then consider, as you said, other experimental designs. So maybe you have like a cool setting where you have regression discontinuity, or there's some kind of within group design. And the thing that's missing is still one needs to consider, what if you don't have the true treatment, but rather a proxy of the true treatment? How can I use it? I think there's definitely opportunities to do really good research there. I don't have like a, I don't have a concrete theoretical result or methodological result, but I think this is a very good avenue to explore.
Thanks, David. Any other final questions for Dhanya? Okay, I think we will wrap up then. Thank you so much for a great tutorial. Please do email her offline and we'll go ahead and post the slides and code so you can all look at it as well in the future. Thanks again, Dhanya.
Awesome. Thank you so much for coming in and for inviting me, Katie and Ian. I guess I'll email the two of you the slides.
That'd be great. Thank you.
Okay, perfect. Okay, awesome. Thank you all so much.